Hello everyone, let's try to implement a stopwatch with pause, play and reset options. Let's begin by creating a new project. The project name will be just stopwatch. Usually it's just an RTL project, so let's just go forward with it. The FPGA board which we currently have, the name of it is XC7S50 CSG324-1. So this is that board. Let's just select it and let's create. So let's just go ahead and add a simulation source, so design source. I'll name it counter. Just explain the code and write it at the same time. Basic idea of the project is to create a stopwatch which runs only when you press the play button and just pauses itself when you press the pause button. So I am planning to achieve this using two modules. One module will be counter and the other module will be to just route the output of this counter to 7-segment display. So the second module will call the first module and achieve the intended functionality. So let's code both of these modules separately. The first module counter takes in all the required inputs: clock, reset, pause, as well as play, and outputs a 4-bit register, Cout. This will be in binary form, which will be converted to as the output of 7-segment display by the second module. So for achieving the counting purpose, I would need two temporary registers, one of 27-bit and the other of just 2-bit. Why exactly do I require it? I'll explain afterwards. So let's begin. Since this counter has to run forever, that is, whenever you press the play button, it should go on counting the seconds, right? So we'll use a forever block, or in other words, always block. I'll configure it to be at the pause edge of the clock. Sensitivity list is the pause edge of the clock, and this Boolean board has an inbuilt clock of 100 MHz frequency. It has a CMOS oscillator of 100 MHz frequency. In other words, in 1 second, it will have 100 into 10 power 6, 10 power 8 positive edges of the clock. So if we can count those number of positive edges, if that count reaches to 10 power 8, then in real world 1 second has elapsed. So using that logic, we will be implementing it. So at whatever time, if reset goes to 1, your counter should go back to 1, pointer should go back to 0, right? And then Cout should also go back to 0. Else, if at any time I get the pause button, I'll assign check variable to be 2-bit 00. In other words, false. Else, if I get a play button, if anybody presses the play, then I'll assign check to be true, 1-1. Else, if at any time the counter reaches 1 after 1 followed by 8 zeros, 10 power 8, 1, 2, 3, 4, 5, 6, 7, 8, then we'll increment Cout by 1. And set counter back to 0. Else, if only check is suppose 1 1. Only then will increment counter by 1. This check is used to achieve that functionality of pause and play. If you press the play button only, then the check will be 1, and then only then the counter will go on incrementing and will count the seconds. Or else if you press the pause, the check will be 0 and the counter will not increment and the cout will never increase. So the purpose of this module is to just increment cout by 1 every 1 second with pause and play options. And this cout is in binary. Now the second module will call the first module and will convert the binary output of first module counter into the output of 7 segment display. Right? So the inputs of this module are clock, reset, pause and play again. It outputs signals to the 7 segment display, which are 8-bit registers. For cathode signals and 8-bit wires for anode signals. So I would need a temporary variable to get the output from the first module. I'll just name it to be cout again and instantiate the first module. Counter, first module name is counter, right? Counter. Let's name the module instance variable to be some block 1. The parameters to it will be clock, reset, pause, play, cout. Right? Now the anode signals will be assigned this 8-bit 7 ones, 5, 6, 7 and 0. This is to this is because we are controlling the rightmost digit of the Boolean board. There are 8 7-segment displays. We are only right now using only one 7-segment display of those 8. So this 0 will denote that we are using only that one, and the other 7 will be off. And for giving the cathode signals, again the sensitivity will again use the always block whose sensitivity is cout. Like whenever cout changes, the 7-segment display should update. Otherwise, there is no need for it to update. Right? We'll use a case instead of if else. It will be easier to understand if we use the case option. And if cout is 0, then cathode will be 8-bit 1, 2, 3, 4, 5, 6. This is just the signals to show which cathode should be on and which should be off in the 7-segment display. It just corresponds to the 0 in the output. Okay, I'm just properly understanding. I'll just type everything and I'll again play. So I've just typed all the 15 possible cases. cout is a 4-bit register, so 2 power 4 will have 16 cases, and all the 16 cases are covered. Just end this case. The end module is always there. Let's just give the constraint file using the design. We'll go to the input-output planning, and so here are the ports. As you can see from the Boolean data sheet, the anode signals are named from A8, C7, C4, D5 to E4, F3, J4, H3. Those signals should be given here. Right? So I'll just give it. This will be A8, C7. I'll just finish it and I'll play the button. And for cathode signals as well, it will be these 8 signals. Or since I'm using this corner 7 segment display, these 8 signals starting from F4 to C1 will be my cathode signals. Those ports I'll just show it. And for clock, it's pin F14. The 100 megahertz clock is connected to pin F14. So I'll just give those input and I'll again so as you can see, I have completed assigning the ports to each and every pin. And let's change the input output standard to LVC MOS 33 as well here. These pause, play and reset buttons are connected to push buttons on the FPGA board. You can see it on the physical board. So let's just save this file by pressing Ctrl S, and I'll give some name, constraint. So that's it. The main part of our designing part is done, and then it's just the program will just run on autopilot. I have to press the synthesis button, then followed by implementation and generating bit stream. I just pause it and come back when the synthesis is done. So the synthesis is done. Let's continue with implementation. The implementation is also done. Let's just generate the bit stream. The bit stream is also generated successfully. We'll just open the hardware manager, connect to the board and just program it. Just show the output once it's programmed.